Greetings of the day to all of you. I welcome you all to second lecture in the series of lectures on over-modulation. In our last lecture, we discussed the over-modulation phenomena in sine triangle PWM. Okay, we have a PWM, we have a three-phase voltage source inverter, and that voltage source inverter is controlled by sine triangle PWM or sinusoidal PWM. And we have seen that for different ranges of modulation in DCs, like for 1 greater than M, 1 less than M, less than 1.15, we have very small depth of over modulation. Okay, that the distortion in the or low frequency distortion in the inverter output voltages is low, and inverter output voltage increases by small amount. And then we consider another range of over modulation, that is 1.15 less than M less than 2, and we found that as we took M equal to 1.2. For M equal to 1.2, we found that the pulse dropping occurs for a period of 60 degrees. Okay, and for a 60 degrees in each half cycle for each phase. And inverter output voltage increases further, but the level of distortion also increases by a little bit. And the magnitude of rotating reference vector, that varies from sector to sector, and in a particular sector also it varies, whereas the angle of rotating reference vector is more or less linear. Then we consider for M equal to 2, for modulation index equal to 2, which is high modulation index or high, which results in high over modulation. We found that the angle for which a particular phase leg has experiences the dropping of pulses or pulse dropping or bus clamping, it's 120 degrees for in each half cycle for each phase. And we found that inverter output voltage further increases, and the level of distortion, low frequency harmonic distortion in inverter output voltages also increases. And we found that the rotating reference vector does not, it traces the trapezoidal path. That means the tip of rotating reference vector moves along the trapezoid, okay, in the space vector diagram, right? And then we found we discussed for M equal to 3, which is fairly high over modulation, and for M equal to 3, we found that the pulse dropping in each phase occurs for more than 120 degrees. Inverter output voltage is very large. It nears 6-step operation. It's not exactly 6-step operation, but it is very close to 6-step operation. And a rotating reference vector magnitude varies. It varies in each sector, and over a line cycle of 360 degrees, it varies. And the angle, the variation of angle is, for some period, the angle of Vref is constant, and then it varies linearly, and then again it is constant. And we found that the rotating reference vector sits at V1 active vector. It applies active vector for some time, and then it moves along the trapezoid, and then it applies active vector 2 for some more time. No null vector is applied, only active vectors are applied. Okay, so that was about M equal to 3. And for M greater than 3, we found that we go to 6-step operation or square wave operation, where each active vector is applied across the load for a period of 60 degrees, right? Now this over modulation phenomenon we will now discuss in 3-phase voltage source inverters, but from space vector perspective. Okay, our domain will not be sine triangle PWM. Our domain of discussion will be conventional space vector PWM. So I will write here analysis of over-modulation. OM I will write in short. OM means over-modulation in conventional space vector PWM. And we will discuss this space vector PWM as in common mode injection PWM, as common mode injection PWM. Because we know that conventional space vector PWM can be implemented through triangle comparison also by injecting a common mode voltage. For example, if your sinusoidal original modulating reference waves are like this is for example MR, this is MY, and this is MB. What we do, if you remember, we inject a common mode signal in the original three-phase modulating waves, MCM equal to 0.5 M mid. Just refresh your memories. I have already discussed with you, and our common mode signal is something like this. This is our common mode signal. Something like this. Okay, this is our common mode signal, MCM equal to 0.5 M mid. And then when this common mode signal, which is equal to 0.5 M mid, is added to all the three sinusoidal modulating waves, our modified modulating waves becomes like this. This is for example for phase R. So this is our MR star. In a similar way, we have MY star, and in a similar way, we have MB star like this. This is MY star, and this is MB star. I have already discussed with you. And then these modified modulating waves, whose amplitude, whose peak value is always less than the original modulating wave. See, original modulating wave has a peak value of, it may be 0.8, but the peak value of modified modulating wave, it may be say 0.7 or 0.6, it's always less than the peak value of original modulating wave. And these modified modulating waves, when they are compared with high frequency triangular carrier wave, they result in generation of gating pulses, and hence they result in switching of devices of the inverter, and that results in the implementation of conventional space vector PWM, and inverter output voltage will be same as obtained in conventional SVPWM technique in space vector domain. Okay, fine. Now, if you take the modulation index equal to 1.15, and we know that in space vector PWM, when we implement space vector PWM, whether in space vector domain or using triangle comparison PWM, by injecting common mode signal 0.5 M mid, okay, the inverter output voltage is increased by roughly around 15.5%. And the original modulation index, M equal to 1.15 means modulation index, that is the peak value of original modulating waves, sinusoidal modulating waves, is 1.15, okay? But the peak value of the modified modulating waves will not go beyond 1. So therefore, from the point of view of original modulating waves, it is over-modulation. But from the point of view of modified modulating waves, it is not over-modulation. So therefore, if you consider conventional space vector PWM as common mode injection PWM, I mean you have three modified modulating waves which can be generated by adding common mode signal MCM equal to 0.5 M mid to each original modulating sinusoidal modulating wave. If you use that implementation of conventional space vector PWM, the original modulating waves will have a peak value of 1.15, whereas the modified modulating waves will not go beyond 1. Okay, so therefore, in the space vector, from conventional space vector PWM point of view, it is not over modulation. Okay, it is under modulation, or it is linear mode of operation. So therefore, our waveforms will be like this. So first of all, I will draw the waveform for three-phase modulating waves, three-phase modulating signals or modulating waves for M equal to 1.15. Remember, M equal to 1.15 means this is modulation index. This is over modulation from the point of view of original sinusoidal modulating waves. But from the point of view of common mode injection PWM or conventional space vector PWM, M will not be 1.15, M will be 1. And let us see what type of waveforms we get. We get the waveforms like this. This is our modulating wave or modified modulating wave, MR star. As you can see, its amplitude is 1.0. I mean, its peak value is 1.0. It will never go beyond 1.0. But original sinusoidal modulating wave will have a peak value of 1.15. So for original sinusoidal modulating wave with peak value of 1.15, the modified modulating wave will have a peak value of 1. So therefore, from conventional space vector PWM perspective, it is not over modulation, it is normal modulation. Okay, so therefore we are not right now considering the over modulation case. We are considering the linear PWM or under modulation case. So this MR star. My star will be like this. My star will be like this. After 120 degrees, we'll have this is our My star. Let me complete the waveform first. So this is my My star, modified modulating wave. How do I get these modified modulating waves? I again remind you by adding a common mode signal MCM equal to 0.5 mmid to all the three original sinusoidal modulating waves MR, My, MB. We get the modified modulating waves MR star, My star and MB star. MB star will be like this. I am using red color for MB star also. This is MB star. So these are our three modified modulating waves, MR star, My star, MB star. What are we doing? We are comparing these modified modulating waves with high frequency triangular carrier wave. For example, your high frequency triangular carrier wave maybe like this. High frequency triangular carrier wave also has a peak value of 1. Okay, so therefore the comparison of the two will generate the control pulses, and those gating pulses are issued to the switches of the inverter, and hence it results in the generation of three-phase output voltages. Let us see the waveform for those voltages. First of all, we'll try to draw the waveforms for three-phase average pole voltages. Three-phase average pole voltages. Three-phase average pole voltages. Let me quickly draw three-phase average pole voltages, and let me tell you that since we are not in the over modulation zone right now, we are in the linear modulation. The three-phase average pole voltages will be scaled version of these modulating waves. So they will have same wave shape as modulating waves like this. Let me draw. So this is instantaneous average pole voltage, VRO average. So this is average pole voltage, VRO. What about V by O? And let me tell you that it has a peak value of 0.5 because when top switch of a particular leg is on, the pole voltage is 0.5 VDC or VDC by 2, and when bottom switch is on, the pole voltage is minus VDC by 2 or minus 0.5 VDC. So therefore the peak values of pole voltage are 0.5 and minus 0.5 per unit. So this is average instantaneous average pole voltage VRO. You can see its shape is exactly same as MR star. So it is basically the scaled version of the modified modulating wave MR star. In a similar way, I can show you the average pole voltage V by O and VBO also. V by O will be like this. This is V by O pole voltage V by O average pole voltage V by O, and average pole voltage VBO will be like this. This is average pole voltage VBO average. You can very clearly see that average pole voltages VRO, VYO and VBO are nothing but scaled versions of modified modulating waves MR star, MY star and MB star, right? Okay, now after this I will show you three-phase line-to-line voltages. I have a space here, I can draw those here. Three-phase average line-to-line voltages or three-phase average line voltages. In the line voltages, the common mode signals cancel, because we know that, for example, line voltage, average line voltage VR by average is equal to average pole voltage VRO average minus average pole voltage VYO average. Okay, and in terms of modified modulating waves, it is MR star minus MY star. What is MR star? MR is original modulating wave, sinusoidal modulating wave plus common mode signal. How do you get MR star? By adding MCM to MR. Minus, similarly, MY star is MY plus MCM. So it is MY minus MCM. MCM cancels, so it is MR minus MY. So therefore your average line voltage, VR by average, is MR minus MY. So that means it is VRO average minus VYO average, and in this the common mode signal does not appear. Since your original modulating wave MR is sinusoidal, original modulating wave MY is also sinusoidal, so line voltages are also sinusoidal in nature. So therefore in the line voltage, although there are distortions in the pole voltage because your modified modulating wave is distorted by the addition of common mode signal. As a result of that, pole voltages also get distorted like this. They are not sinusoidal. But line voltages and line to neutral or phase voltages are purely sinusoidal, because this common mode signal gets cancelled in both line voltages as well as phase voltages. So let me draw three-phase line voltages, average line voltages. Just like this. So this is 1.0 minus 1.0. This is line voltage VR by average line voltage VR by. Similarly, average line voltage will be V by P average, and third average line voltage will be like this. This is VBR average. So you can very clearly see that although pole voltages are non-sinusoidal, but line voltages are purely sinusoidal, and they have a peak value of 1. Okay, what about three-phase average line to neutral voltages or three-phase average phase voltages? They will also be sinusoidal because common mode signal will cancel in them also. Three-phase average phase voltages or line to neutral voltages, they will also be sinusoidal. Like this, you can draw them. Have a peak of around 0.5, rather they have a higher peak. The peak value is 1 by root 3, which is equal to 0.577. This ये आपका 0.6 है, ये line 0.6, and peak of the phase voltage VR and average will be 1 by root 3, that is 0.577. It's higher than 0.5. Similarly, you can draw average phase voltage. This is VYN average, and in a similar way you can draw VBR average, average phase voltage, VBN average. Okay, and, and if you compare the pole voltage and line phase voltages, you take just one cycle of pole voltage. Your pole voltage, just few moments back you have seen, it is like this for phase R. For example, this is your average pole voltage, VRO average. It has a peak value of 0.5. But your average line voltage will be like this. Average phase voltage, not line voltage, will be like this. This is phase voltage VRN average. You can see its peak is 0.577, which I have already shown here. It is 0.577. It is higher than pole voltage peak. Okay, so that was about pole voltage, three-phase average pole voltage. So that means for under modulation, we are not now in over modulation mode, we are in linear modulation mode. The phase voltages and line voltages are purely sinusoidal. Okay, now what will be the magnitude of average rotating reference vector, rotating reference voltage vector, or rotating reference vector, which is also called VREF, over a cycle, over a line cycle. You take, omega t 0 degree to 360 degrees, and you take the amplitude of rotating reference vector. It will be constant like this. It is absolutely constant. It does not vary. Okay. And then what about the variation of angle? Variation of angle of rotating reference vector over a sector. Over a sector. The rotating reference vector, for example, this is omega t, say 90 degrees to 150 degrees, you may take one sector, and it varies linearly. This is the angle alpha. It varies linearly. So that's it. And therefore, what is the average voltage vector applied across the load in terms of space vector? Average voltage vector applied. So average voltage vector, for that you have to draw the space vector diagram. So this is my space vector diagram. This is active vector 1 with switching sequence plus minus minus, active vector 2 with switching sequence plus plus minus. Similarly, active vector 3 minus plus minus, active vector 4 minus plus plus, active vector 5 minus minus plus, active vector 6 plus minus plus, null vector 0 minus minus minus, and null vector 7 plus plus plus. And this is the regular hexagon when the tips of these voltage space vectors are joined. It becomes hexagon. Okay, so this is the circular trajectory which will be traced by average rotating reference vector. Just like this. So my average rotating reference vector, VREF, let me call this VREF1, it will be this, and then next sample will be here, next sample will be here, next sample will be here, here. It will follow this circular trajectory, and then active vector 2, and then like this, it will follow circular trajectory. So it will follow absolutely circular trajectory. So this is the circular trajectory which it will follow. Okay, and angles will be constant. This is omega ts, this is omega ts. So it will be constant. And the length of this rotating reference vector, so it will be 0.866 VDC. This will be the length of this rotating reference vector. So it will trace the tip of the rotating reference vector will trace the circular trajectory, which means there are no distortions in the inverter output voltage, and that is true. Okay, so that is about, for m equal to 1.15. So which means over modulation with respect to original modulating wave, but with respect to conventional space vector PWM, it is not over modulation. It is under modulation. For conventional space vector PWM, your modulation index is 1, because you have just now few moments back seen that these modulating waves, modified modulating waves, MR star, MY star, MB star, their peak value is 1. They don't go beyond 1. So therefore, M star is 1. Okay. Now let us see what happens when we go into the over-modulation zone, okay, in space vector domain. So for that purpose, I will take first range of this. I will take over-modulation in the range 1.15 less than m less than 1. Is it 1.33? Let me verify. Yeah, 1.33. That means now modulation index is greater than 1.15 but less than 1.33. As soon as your modulation index m becomes greater than 1.15, your inverter will go into over modulation. From the point of view of conventional space vector PWM, it will go into over modulation. Let us take modulation index equal to 1.2, which is of course greater than 1.15. So our inverter will now go into over modulation. So therefore, our three-phase modulating waves, let us draw three-phase modulating wave. I am not writing three-phase sinusoidal modulating waves because our modulating waves are no longer sinusoidal. By the injection of common mode voltage 0.5 and mid, our modified modulating waves are non-sinusoidal. But now here m is equal to 1.2. So we are now considering over modulation. Okay, first of all, we will have MR star. Let me draw MR star first. This is modified modulating wave MR star, which is MR plus MCM. Anyway, we know that. I don't need to repeat it again and again. Now I will draw MY star. By the way, what is this peak value? This peak value is not 1 now, it is 1.2. Its peak value is 1.2 and 1 is somewhere here. This is 1. This is 1. Now you can clearly see that it is over modulation because the peak of reference wave or peak of modulating wave is greater than peak of carrier wave. Peak of carrier wave is 1. So it is greater than that during these instants. So this is a case of over modulation. Fine. So let us quickly go for similarly in the negative half cycle. Let me first show you this minus 1.2. Let us quickly draw second modulating wave. This is MY star and now MB star. It will also touch 1.2 peak. This is MB star. So you can see MR star, MY star, MB star, they are greater than 1. Their peak is greater than 1. M is 1.2. 1.2. What will be the nature of average pole voltages? Now our average pole voltages will not be exactly same as modulating waves because of over modulation. Let us see what will be the nature of average pole voltages. Right now, three-phase average pole voltages for M equal to 1.2. Okay, so average pole voltages will be something like this. Let me quickly show you three-phase average pole voltages. Let me first of all draw pole voltage VRO average. It will go like this, and then it will be constant. It will be, clipped. It will be clipped again for around 60 degrees. There is pulse dropping here. There is pulse dropping here also. Similarly, in the negative half cycle, clipping here, and then again clipping. So this is 0.5, and this is minus 0.5. Because when your MR star is going greater than peak value, say for example your triangular carrier wave is like this, but your original modulating wave is going above this. What will happen during this period? Since the modulating wave MR star is greater than triangular carrier wave, so top switch of phase lag R will be permanently on during this period. And when top switch is on, what is the pole voltage? It is 0.5 VDC. Okay, so therefore since pole voltage cannot be greater than VDC by 2, its maximum value is VDC by 2, that's 0.5 VDC. So therefore during this over modulation period, our average pole voltage will be VDC by 2 or 0.5 VDC. So it will get clipped. It cannot be more than VDC by 2. So that's why it gets clipped like this. So there is pulse dropping here, there is pulse dropping here, or bus clamping. Similarly, in the negative half cycle, pulse dropping takes place here and pulse dropping takes place here. So this is average pole voltage, VRO average. What about average pole voltage, VYO average? Okay, VYO average will be like this. Let me first of all extend this 0.5. Okay, fine. So it is very easy to draw now. Clamping or pulse dropping, and then again pulse dropping. Similarly here, pulse dropping. So this is VYO average, pole voltage VYO average, average pole voltage VYO. And VBO will also be like this. Pulse dropping and then again pulse dropping. Excuse me. This is VBO average. Now you can see during this interval, I mean from here to here, let me call this point as X and this point as Y. Between X and Y, phase lag R, okay, this phase lag R is clamped to positive DC bus and phase lag Y is clamped to negative DC bus. What about phase lag B? It is not clamped, it's switching. So R phase is not switching, Y phase is not switching, only B phase is switching. So I will write here between instants X and Y, that is this point and this point. See, VRO is 0.5 VDC, VYO is 0.5 minus 0.5 VDC. So that means neither R phase, there is pulse dropping in R phase, there is pulse dropping in Y phase because of over modulation. In other words, R phase is clamped to positive DC bus, Y phase is clamped to negative DC bus. So neither R phase nor Y phase is switching. But which phase is switching? B phase during this period is switching, you can see. So between X and Y, only B phase switches. Whereas R and Y phase, they do not switch. Okay, so only one active vector is applied. Only one active voltage vector or active vector is applied. And if you find the tip of rotating reference vector, it will follow hexagonal path, hexagonal trajectory. And tip of reference vector or reference rotating vector touches the hexagon. Okay, fine. On the other hand, अगर आप यहाँ पे देखेंगे, if you see during this interval, यहाँ से यहाँ तक देखें, we first correct it. अब आप यहाँ से यहाँ देखें, from this instant to this instant. यहाँ से यहाँ आप देखें, see R phase, ये clamp नहीं है, R phase clamp यहाँ तक है. So R phase is switching. What about Y phase? Y phase is also switching. And what about B phase? B phase is also switching. क्योंकि ये clamping यहाँ तक है, उसके बाद ये circular, ये नीचे जा रहा है. So therefore R phase is switching. It's not clamped. Y phase is also not clamped. It's switching, and B phase is also not clamping. It is not. It's not clamping. It's not clamped. It's switching. So let us call this interval 1 or period 1 and period 2. So between 1 and 2, you can see all the three phase legs switch. So between 1 and 2, all the three phase legs switch. All the three phase legs are switching. So this means active vectors are applied and null vector is also applied. Active vectors and null vector are applied. Say for example, if you are sector 1, active vector 1, active vector 2 and null vector 0 and null vector 7, they are applied. So therefore, when all the three phases are switching and active vectors and null vectors are applied, then you find that trajectory of rotating reference vector will be circular. Okay, so during this period, I will write during this period, that is between 1 and 2, average rotating reference vector follows a circular trajectory. Follows a circular, not hexagonal trajectory, but circular trajectory. So therefore, your rotating reference vector will be partly following, you tracing the circular trajectory, and partly it will be tracing the hexagonal trajectory. I mean, over long periods, and pulse dropping is there for about 60 degrees here and 60 degrees. So over these pulse dropping intervals in positive half cycles as well as in negative half cycles, only one active vector is applied, because only one phase is switching, two phases are not switching. There is pulse dropping in two phases. So rotating reference vector will follow the hexagonal trajectory. However, during these small intervals, this interval, okay, and similarly this interval, for example, I have shown here, during this interval, all the three phases are switched. There is no pulse dropping at all in neither of the phases. And since all the three phases are switching, active vectors and null vector are applied, and your rotating reference vector follows the circular trajectory. So therefore, just in a minute's time, I will show you, we will draw the space average voltage vector applied, and I will show you that the rotating reference vector partly follows the circular trajectory and partly it follows the hexagonal trajectory, right? So that was about three-phase average pole voltages. What about three-phase average line voltages? Let's quickly draw them. Three-phase average line-to-line voltages or average line voltages. So your three-phase average line voltages will look like this. For this is, we are considering m equal to 1.2, which is over modulation. Okay, something like this. This is VRY average. This is VYB average, and this is VBR average. Similarly here. This is VBR, three line voltages, VRY average, VYB average, VBR average, three average line voltages. So peak value is 1 and -1. Now you can see during over modulation period, pulse dropping is there. So, line voltages, they are, they remain at higher value, 1. They are clamped, or they apply 1 every this line voltage across the load for this may be around 60-degree interval. Okay, so this is about, and you can see that your line voltage is not now sinusoidal. Okay, it is non-sinusoidal because it is flat topped here. It's not, I mean, had it been sinusoidal, that it could have been like this. I mean, sinusoidally vary. Its peak could have been like this, but its peak is flattened here. So positive half cycle and negative half cycle for all the three phases. So your line voltage introduces some low frequency distortions because line voltages are distorted. What about three-phase line to neutral voltages, or three-phase, phase voltages? Your phase voltages will also be distorted. Three-phase average phase voltages. Three-phase average phase voltages. So they will be like this. They will also have, they will also be clipped near the peaks. So this is average phase voltage VRN average. This is average phase voltage VYN average, VYN average, and this is average phase voltage VBN average. We first of all complete. This is VBN average, right? So these are our average three-phase average phase voltages, right? Now what about magnitude of average vector? Magnitude of average reference, rotating reference vector, that is VREF over a line cycle. Over a line cycle. This is omega t 0 degree up to 360 degrees, and this is magnitude VREF. Something like this. One, two, three, 4, 5, 6. So this is 360 degrees, right? And this is 0.8, for example. This is 0.8 and this is 1. So you can see average rotating reference vector. It's not constant. It remains constant for some period, and then it varies. In fact, it remains constant when your rotating reference vector follows the circular trajectory, and then it varies when it follows the hexagonal, this trapezoidal trajectory. Then it is again like this, and if you see magnitude of VREF over one sector, this is over complete cycle 30 to 360 degrees. What about over one sector or over a sector? It will be like this. You can take sector 90 degrees to 150 degrees. From 90 degrees to 150 degrees, VREF will vary like this. It will start, say for example, it will be constant, then it will dip, and then it will again remain constant. So here, when it is constant, active vector V1 is applied. When it is, this is now our 150 degrees, omega t, and this is 150 degrees. When it is constant, again, active vector V2 is applied. And when it follows circular trajectory, there is switching between V1 and V2. Switching between active vector 1 V1 and active vector 2 V2 takes place during this instant of time, during this period. And what about angle of rotating reference vector? Variation of angle of average rotating reference vector. Rotating reference vector over a sector. For example, we may take again sector 90 degrees to say 90 degrees to 150 degrees, and this is alpha angle, so it varies linearly from 90 to 150 degrees. It varies linearly, so varies linearly, which means that your rotating reference vector moves at a constant speed. Okay, this is the meaning of it. What type of average voltage vector will get applied across the load? Let us see. Average vector applied. Average voltage vector applied across the load. Average voltage vector applied. So average voltage vector will be like this. Let us draw the space vector diagram. This is active vector 1. This is active vector 2. This is active vector 3. This is active vector 4. This is active vector 5. And finally, this is active vector 6. This is null vector 0. This is null vector 7. And this is our hexagon. Okay. Near these edges, it will be circular like this. Circular, circular, circular like this. Circular, circular. Therefore, your reference vector, when your reference vector starts rotating, I mean your reference vector may be somewhere here. Let us call this Vref1. Then it is here. Let us call this Vref2. Then it is here. Then it is here. Then it is here. Here. We can see from here to here it is following circular trajectory. And it is following circular trajectory. Just few moments back I have discussed with you through the waveforms. It is following these circular trajectories over those small intervals of time when all the three phases are switching. Phase leg R, phase leg Y and phase leg B. All the three phase legs are switching. Those instances when over-modulation, effect is not there. When all the three modulating waves, MR star, MY star, MB star are less than triangular carrier wave, and all the three phase legs are switching. All the three legs are switching. And then over larger intervals of time, when only one phase is switching, only one active vector gets applied, no null vector gets applied. And when only one phase switches, for example, I have shown between X and Y, phase leg R, phase leg Y, they are clamped, there is pulse dropping, but phase leg B switches. And when only one leg switches, one phase leg switches, then rotating reference vector does not follow the circular trajectory, it follows this trajectory, hexagonal trajectory. It moves along the hexagon, and then again it moves along the circle like this. So this happens in one sector and this happens in all the sectors. So therefore the trajectory of rotating reference vector is partly circular and partly hexagonal. Okay. So here during this interval, ये जो आपका ये circular मैंने draw किया यहाँ, circular trajectory, during this period the rotating reference vector trajectory is partly circular trajectory, but during a larger interval of time its trajectory is hexagonal. You can see I will write here during this period when there is pulse dropping in two phases and only one phase switches, the rotating reference vector moves along the hexagon, side of hexagon. So trajectory is hexagonal. I will write here partly hexagonal trajectory. So I hope this is clear. Okay. So let us summarize what we have observed in this range. Summary. Summary is for 1.15 less than m less than 1.33. when m is greater than 1.15 but less than 1.33. For example, we had taken m equal to 1.2, which is greater than 1.15 but less than 1.33. When modulation index is between 1.15, greater than 1.15 but less than 1.33, following points you have to note. I am writing some points which you have observed through the waveforms. First point is no modulating wave, no modulating signal, or two modulating signals or modulating waves, or two modulating signals exceed carrier peak in a given carrier cycle. Let me remind you, when we had considered that x and y, in that between x and y, you had seen that there is pulse dropping in two phases. The pulse dropping in two phases occurs because two modulating waves exceed carrier peak, and one leg was switching because its modulating wave was less than carrier peak. And then I have shown you small time period between 1 and 2, during which all the three modulating waves are where their peaks were less than the carrier peak, and all the three phase switches were they were switching. Okay, so therefore at any instant of time you will find no modulating signal or two modulating signals exceed carrier peak in a given carrier cycle. Okay, second point is that all three phases switch. I mean, if there is no modulating wave peak is greater than carrier peak, then all the three phases will switch. Or if this is the situation that two modulating signals exceed carrier peak, then only one phase leg will switch and there will be pulse dropping in other two phases. So I have written here all three phases switch, or only one phase switches. Only one phase switches. Okay, and then pulse dropping around two peaks. Okay, that we have already noted. Then low frequency distortion or low frequency harmonic distortion in output voltages. You have seen your phase voltages as well as line voltages, they get distorted. So there is some level of low frequency harmonic distortion of inverter output voltages. And we have noticed one more important point about the rotating reference vector, that is magnitude of rotating reference vector Vref varies with fundamental angle. So this was another observation. It's not constant. And we have also found that trajectory of the tip of rotating reference vector, that's Vref, trajectory of the tip of Vref is partly circular and partly hexagonal. Right? And what about angle of Vref? Angle of average rotating reference vector Vref almost varies linearly with time or with fundamental angle. So that means rotating reference vector, whether it is tracing circular trajectory or hexagonal trajectory, its speed is constant. Its angle varies linearly. Okay. So that was about, if we are considering over-modulation with, modulation index greater than 1.15 but less than 1.13. We have seen that rotating reference inverter output voltage no doubt increases, but low frequency harmonic distortion is introduced in inverter output voltages. At any instant of time, either one phase will be switching only, or all the three phases will be switching. And magnitude of rotating reference vector varies with time, and trajectory of rotating reference vector is partly circular and partly hexagonal. Fine. Let us take some higher value of modulation index. We will take m equal to 1.33. So over modulation with m equal to 1.33. Previously we had taken m equal to 1.2, which was greater than 1.15 but less than 1.33. Now let us take exactly m equal to 1.33. So your reference waves will be like this. Three-phase modulating waves will be like this. This is MR star and its peak is now 1.33, right? And this is 1. This is 1, carrier peak 1. But its peak value of MR star is 1.33. It's greater than 1. You can very clearly see. Fine. So this is MR star. What about MY star? MY star is also over-modulated. And MB star is like this. This is MB star. So you can see from this instant to this instant, from this instant to this instant, ये instant, यहाँ से यहाँ तक. Do you know how much is this time period? This time period is 120 degrees. During this entire 120 degrees, the peak of reference wave MR star is greater than triangular carrier peak, which is 1. Because it is 1.33 and triangular carrier peak is 1. So from this instant to this instant, MR star is higher in amplitude than carrier peak, and this period is 120 degrees. So there, that means in phase leg or in positive half cycle, there will be pulse dropping for 120 degrees. Similarly, in the negative half cycle also, यहाँ से यहाँ तक 120 degrees है, there will be pulse dropping for 120 degrees. So in each half cycle, for each phase, there will be pulse dropping for 120 degrees. So it will be clear to you if you, and you have seen, if you remember, this pulse dropping for 120 degrees was, we had observed in sine triangle PWM with over modulation, but what was their modulation index? Modulation index was 2. So I will write here, this is similar to modulation index equal to 2.0 in sine triangle PWM. Sine triangle PWM. In previous class, we discussed over modulation with sine triangle PWM, and there we found that when modulation index is 2 for over modulation, when modulation index is 2, then pulse dropping for 120 degrees takes place. But in space vector PWM, for 120 degree pulse dropping takes place for smaller modulation index. Here modulation index is 1.33, not 2. Okay, so in space vector PWM, for m equal to 1.33 gives similar effect as m equal to 2 in sine triangle PWM. Because in sine triangle PWM, m equal to 2 gives pulse dropping for 120 degrees, and in conventional space vector based PWM technique, 120 degree pulse dropping occurs for m equal to 1.33. It will be more clear to us if we draw the waveforms for average pole voltages, etc. I will draw three-phase average pole voltages. I will draw all the three pole voltages, average pole voltages, VRO average, VYO average, and VBO average. Let me draw first VRO average. So this is for 120 degrees. You can very clearly see, ये आपकी 0.5 है, because your pole voltage cannot be more than 0.5. Okay, so this is pole voltage VRO average pole voltage VRO, pulse dropping is there for 120 degrees. Fine. What about VYO? VYO will be, let me extend this. This is pole voltage VYO, average pole voltage VYO, VYO average. What about VBO? This is VBO average, pole voltage VBO, VBO average. It's like this. Okay, so this is VRO average, VYO average, VBO. You can see VRO average is, clamped to positive and negative DC bus for 120 degrees each. Similarly, VYO average, VBO average. So there is pulse dropping for 120 degrees in each half cycle. And you can very clearly see that average pole voltages get distorted. They are no longer sinusoidal. Okay, and they don't even follow your modified modulating waves, because your modified modulating waves are something like this. Because of over modulation, pulse dropping, they are like this. Okay, so this was about three-phase average pole voltages. What about three-phase average line voltages? Let us quickly draw three-phase average line voltages. So our three-phase average line voltages will be like this. So this is 1.0 and this is minus 1.0. You can extend it. Okay, so this is line voltage VRY, average line voltage VRY. What about VYB? This is line voltage VYB average, and VBR average is like this. So this is average line voltage VBR average. So you can see, the line voltages are at 1.0 for a longer period of time. So when they are at 1.0 for a longer period of time, that means RMS value of inverter output line voltages across the load increases, because they stay at 1.0 for more time. So that will increase the magnitude of line voltages applied across the load. So inverter output line voltages will increase because of over modulation. Okay, so what about three-phase line to neutral voltages, or three-phase average phase voltages? Three-phase average phase voltages. Three-phase average phase voltages will be like this. So this is, for example, ये आपका 0.6 है यहाँ. This is 0.6 and this is minus 0.6, and this is phase voltage VRN average. VYN average will be like this. This is VYN average, and VBN average will be like this. This is VBN average. Now we can compare average pole voltage and average phase voltage. Okay, you can compare the two. For example, let us take average pole voltage. This is average pole voltage, omega T. So this is average pole voltage VRO average. It's 0.5 minus 0.5. And average phase voltage will be like this. So this is average phase voltage VRN You can see its peak is higher, it's more than 0.5. Okay, so therefore our phase voltages also are distorted, right? Now we can draw the variation magnitude of average reference rotating voltage vector Vref over a line cycle. It will vary like this. This is 360 degrees omega t, and this is 0 degree, and this is touching 1. Okay, this is 0.8 and this is 1. And if you take over one sector, magnitude over one sector, it will be like this. For example, you can take 90 degrees to 150 degrees, and this is Vref magnitude. This is also Vref over one sector. It is like this, varies like this. This is 90 degrees to 150 degrees, 1.0. Okay, it varies like this. Okay, so therefore, what about the variation? Variation in the angle. Variation of angle of rotating reference vector Vref over a sector. It varies linearly. For example, this is omega t 90 degrees to, say, for example, 150 degrees, and this is angle alpha. It varies linearly, 0 to this. It varies linearly. Okay, so varies linear. That means your rotating reference vector moves at a constant speed. Okay, well, let us see now the nature of average voltage vector applied across the load. Average voltage vector applied. What type of average voltage vector is applied? Let's draw the space vector diagram. This is active vector 1, similarly active vector 2, active vector 3, active vector 4, active vector 5, active vector 6, and these are null vectors 0 and 7, and this is our hexagon. You will find that our rotating reference vector will move along the hexagonal trajectory. It will not trace circular trajectory at all. It will not trace circular trajectory, and no null vector will be applied. Okay, so this is omega ts, this will also be omega ts, so angles will remain same in each sample. The speed at which rotating reference vector moves, it will remain constant. Okay, so it will trace the hexagonal trajectory. And if you find peak of fundamental component of inverter output voltage, that will be 95.2% of that of 6-step voltage source inverter peak. Okay, so this is same as for sine triangle PWM with m equal to 2. And remember one more thing, no null vector is applied. Only active vectors are applied. No null vector is applied. For example, in sector 1, active vector 1, active vector 2 only are applied. No null vector 0 or 7 is applied. In sector 2, active vectors 2 and 3 are only applied. Okay, so this gives same result as given by sine triangle PWM with m equal to 2. Okay, fine. So let us summarize our observations for m equal to 2. Summary. First point is two modulating signals exceed the carrier peak in any given carrier. Whereas you have seen previously, if your modulation index is greater than 1.15 but less than 1.33, two modulating signals may exceed the carrier peak in a given carrier, or no modulating signal may exceed a carrier peak in a given carrier, which gives rise to only one phase switching or all the three phases switching. But here in this case, for m equal to 1.33, at any instant of time in a given carrier, two modulating signals will be exceeding the carrier peak. Okay, that means only one phase will be switching. Only one phase switches between active vectors. No null vector is applied, only active vectors are applied between active vectors. Only one phase at any instant of time will be switching, and two phases will be having pulse dropping or bus clamping. Okay, and for how much period pulse dropping takes place? Pulse dropping for 120 degrees duration occurs in each half cycle. In each half cycle for each phase. We have just now observed few minutes back this. And low frequency harmonic distortion will be there. Low frequency harmonic distortion in output voltages. That is three-phase output line voltages and three-phase output phase voltages. Three-phase output voltages. Okay. And what about trajectory of rotating reference vector? Trajectory of reference vector is fully hexagonal, not circular at all, is fully hexagonal, which means there is a lot of distortion in the inverter output voltage. Okay, what about angle of average rotating reference vector? It almost varies linearly, almost linearly with time. And what about magnitude of Vref? Magnitude of Vref varies with angle, with fundamental angle. It's not constant, it varies. Okay, this is called over-modulation zone 1. So therefore, I will write here one very important point that for m equal to 1.15 to 1.33, we get over-modulation zone 1. This is called over-modulation zone 1. In space vector terminology, it is called over-modulation zone 1. For example, you have seen when m is greater than 1.15 but less than 1.33, we get some sort of over-modulation. Inverter output voltages increase. Either no phase or two phases exceed the carrier. Either no modulating signal or two modulating signals exceed the carrier peak. That means either only one phase switches or two phases or all the three phases switch. And then, for m equal to 1.33, we get the same results as for m equal to 2 for sine triangle PWM. That is, pulse dropping occurs for a period of 120 degrees. And at any instant of time, two modulating signals will be exceeding the carrier peak. That means only one phase leg will be switching, and trajectory of rotating reference vector will be hexagonal. Whereas for m less than 1.33, it will be partly circular, partly hexagonal. Okay, this is called over-modulation zone 1 if your modulation index is between 1.15 up to 1.33. It's called over-modulation zone 1. And if m is greater than 1.33, we get over-modulation zone 2. We get over-modulation zone 2. I mean, our inverter will be operating in what we call as over-modulation zone 2. Now we are going to discuss that over-modulation zone 2 in the next class. So please go through this lecture, and in case of any doubts, you want any you have any queries, please put your queries on the group. Thank you.